let me just announce while I'm waiting for Pedro to come back that all the presentations you're seeing today and tomorrow, all these slides will be up on the website. We have a whole page on the conference and so forth. And then the plan will be, and I'll introduce Casey, the intern from Rice, who's been working on this project. The plan will be to try to put together a conference report that maybe will add some materials. We may come back to some of you speakers to help us have the write-up be, highly informed and so forth, maybe more informed than you can do in a short presentation. So with that, let me introduce Pedro Alvarez, who is our chairman of Civil and Environmental Engineering, and he is going to talk about ethanol and fuel, microscopic and macroscopic implications for groundwater.
Thank you, Amy. It's a pleasure to be here and have this opportunity to welcome you to Rice. As you probably know, ethanol is playing a key role in many discussions that involve energy, agriculture, taxes, and the environment. And today I'm going to focus on the latter, on the environment. With a particular subset of these discussions, we're going to look at how fuel ethanol, what is the use of ethanol in fuel means to groundwater pollution, and I'm going to be presenting primarily some research, some results that has been conducted at multiple scales, from the microscopic scale where we look at its effect on microbial enzyme induction and so on, all the way to larger field scale studies that look at the behavior of groundwater pollution by fuel ethanol and the associated pollutants. Primarily, we're going to look a lot at the focus at the fate of the monoaromatic hydrocarbons, benzene, toluene, ethylbenzene, and the trisilene isomers, which are collectively known as the BTEX. As you know, these are the most soluble and the most toxic components in gasoline. So we're most concerned about how ethanol might, by way of outline here, how ethanol might influence the mobility of these compounds and their biodegradation as well. Okay, and the focus is going to be primarily on benzene, because this is the only one that is carcinogenic. Benzene can cause leukemia. The other ones are of little concern. Before I begin, I want to acknowledge many students that obtained the data that I will be presenting here, primarily Dr. Marcio da Silva, who's sitting over there, and also many colleagues that were great sources of discussion and collaboration, including Sue Powers, who is also one of our guests today. And of course, I have to thank many, many funding agencies. When we started this program about 10 years ago, this was a very poorly funded area. It wasn't on many people's radar screen, so you had to be an oligotroph and get a little money from here and a little from there to try to get going. Fortunately, that's changing over the past years. But by way of beginning, let me remind you that urban air pollution is at the forefront of environmental concerns, and this is a problem that is partly created or partly due to automotive emissions. And there are many people, many scientists all over trying to work how to reformulate gasoline better so as to minimize this problem without compromising performance. And in the United States, the Clean Air Act of 1990 mandated the use of certain oxygenates like MTBE, which make the combustion process cleaner. They reduce at least carbon monoxide and hydrocarbon emissions. And the use of MTBE, together with catalytic converters, did wonders for air quality, as you can see in these before and after pictures in LA. So it did have a positive effect, but as is often the case in engineering, often the solution to one problem creates another one. There is some collateral damage. And in this case, the presence of MTBE in gasoline exacerbated groundwater pollution by petroleum product releases. We have 2 million underground storage tanks in the US. 450,000 have been confirmed to be leaking. Approximately 11 million gallons of gasoline leak every year and contaminate our drinking water resources with these compounds such as benzene that are carcinogenic. The problem is that the modern gasoline, reformulated gasoline with MTBE, whose structure is shown here, forms even longer groundwater plumes, larger contaminated areas, because MTBE has a couple of xenophores. That's the name we give to functional groups that make a molecule resistant to microbial degradation. We have an ether bond and a tertiary carbon. So MTBE, besides being very soluble, is not biodegraded easily. And that results in impacts that are very large. MTBE is also now present in our rainwater. So, Lake Tahoe has MTBE not only because of the boating activities, but also because it rains. And it is a potential carcinogen that also has adverse aesthetic impacts since it smells and tastes like turpentine. So, as you probably know, people are phasing out MTBE, and ethanol is being increasingly used to meet clean air and renewable fuel requirements. The proponents correctly argue that it does reduce air pollution, although those of you that have been to Sao Paulo, you probably have smelled that aldehyde strength, so it does reduce carbon monoxide and hydrocarbon emissions, but there is a little bit of a problem with aldehyde that we should not forget. It is a renewable resource that's consistent with the sustainability paradigm. It is biodegradable, so it shouldn't last that long. Even methanol, we were talking a little bit later, we buy methanol in wastewater treatment to promote the eutrophication, so I don't think it will be any problem whatsoever if the students dump it in the sink. It's very biodegradable, and it's a resource for wastewater treatment. It helps remove nitrates. But anyways, going back here, it is non-toxic, unless you drink it in excess, of course, and it can serve as a substitute fuel for imported oil. This is one of the things we learned well from Brazil. Jamaica is also trying to implement a large ethanol program. You could argue that it provides some strategic independence from imported oil, that it is also stimulates rural agriculture, which is good for food security, and many positive things. But of course, there are people that also object to, for example, the fact that on a philosophical ground, you're trading food into fuel, or others object to the tax subsidy, and they question whether that amounts to corporate welfare for corn growers and ethanol producers. So it's not a very clean-cut issue here. What are the pros and cons? I see our roles as professors and scientists as primarily providing scientific input to decision makers. And with that in mind, the issue or question that I want to address today is related to groundwater pollution, and is how does ethanol affect the migration and the degradation of BTEX compounds, and what is the overall effect on the plume length? Because the plume length determines the likelihood that the contaminant will reach a receptor. So are we at an increased risk? And if so, is this risk significant or not? Before, just some very quick background, I want to tell you a little bit about the life cycle of plumes of a spill. When a contaminant is released from a gasoline station, for example, benzene, it will form a plume that will begin to migrate in the direction of groundwater. And in the process, many physical, chemical, and biological processes may act upon the contaminant, such as volatilization, sorption, and mainly biodegradation, reducing the overall mass and toxicity of the compound. When these processes act without human intervention, without engineered enhancement, this is called natural attenuation. So what will happen is that a benzene plume typically will extend to a maximum length of maybe 200-300 feet, and it will stay put there. It will reach a steady state that may last 20, 50 years, depending on the scenario. And that happens when the rate at which the contaminant is introduced or released into the aquifer is the same as the rate that it is being naturally attenuated, right? So that's what is called natural attenuation. Obviously, compounds that have more xenophores, that are more recalcitrant to degradation, they make larger plumes. MTBE plumes, for example, will be 1 to 10,000 feet long, as opposed to 100 feet to 200 feet for benzene. So eventually, you do remove the source, and then the rate of introduction becomes lower than the rate of degradation, and the plume begins to shrink until it goes away, and that's the life cycle of a plume. So when we talk about natural attenuation, this is precisely what I'm referring to. Now, very quick review. You guys brought up the issue that ethanol is hygroscopic. You don't want to have water in your tank. Therefore, you don't mix ethanol with gasoline at the refinery. You do that at bulk terminals, unlike MTBE. So there's two scenarios that are of interest here. One of them is the release of neat ethanol, which contains 5% of gasoline as a denaturant to make it unfit for human consumption. If you didn't do that, then people will be having parties in gasoline stations as they used to do in Rio de Janeiro, Marcio tells me. And But anyways, the problem is that you can have this release of neat ethanol, or you could have releases of ethanol blended fuels, like, for example, the gasohol that they're increasingly using in the Midwest, in the Chicago area, or even in Colombia now. So we're going to look at those two scenarios. First, we're going to start with the physicochemical effects. How does the spill behave? Right behind my office, we have these large construction dumpsters that are heavily monitored that we use to simulate at a near field scale releases of contaminants. The advantage of this system is that at a lower costs that you would have to incur in a field scale study, you can get excellent mass balances, which is important to have credibility in your results. And we have a window to see what is going on, and we are E95, that's ethanol with 5% gasoline as a denaturant, and we try to see how it behaves. As you know, ethanol is one of those compounds that are reduce the polarity of water and have a co-solvent effect, and they can mobilize hydrocarbons, right? So what happens is this black here is an acrylic wall that we put here to force ethanol to go to the water table. The water table is right about here. And we add a dye that is hydrophobic, a Sudan red, which sticks to the hydrocarbon. This is a technique actually we copied from Susan Powers. And the idea here is to see how it behaves. And the ethanol clearly goes into the water, carries along with it the hydrocarbons, but then it's sucked up by capillary forces. And the interesting thing also, part of it is the buoyancy of ethanol. So what happens is that ethanol decreases the surface tension in the capillary fringe, and this facilitates movement through the capillary forces. But eventually, ethanol gets diluted by water to a point that its co-solvent effect is diminished, and then this causes the separation of the hydrocarbon oily phase, what we call the NAPL, the non-aqueous phase liquid. So what's important about this? The important is that ethanol creates a source zone. It spreads out and distributes the hydrocarbons. Ethanol eventually washes out and leaves the system, but it leaves behind the denaturant, which contains benzene and other compounds of concern. So this is creating a source zone that bleeds off slowly and keeps contaminating the groundwater for a period after the ethanol is long gone. We see when we analyze the effluent of the tank what's coming out, we see that the ethanol, well, we get very good recovery, near 100%, that lends credibility to the result. But the important thing is that ethanol is coming out slower, traveling 10 times slower than the water. And that surprised me because ethanol is very soluble. It's supposed to be completely miscible in water. So why isn't it traveling at the same velocity of water? Well, the reason is because it's not really traveling in the saturated zone. It's going slower through the capillary fringe. And we can see here when we look at the concentration profiles, ethanol actually primarily travels through a thin layer compared to the bromide tracer. But the important impact here to remember is that ethanol, even though it will be gone from the system in a month or so, it will be degraded or diluted away, it will leave behind a footprint of the hydrocarbons that were present initially with it. Now, regarding biodegradation, which I think is the most influential process in natural attenuation, we conducted experiments with chemostats. Chemostats are essentially flow-through reactors that are completely mixed. You can run them at steady state so that you can isolate the effect that a substrate may have on a particular biochemical process, for example, enzyme induction. And what we're looking at here on the y-axis is the rate at which toluene, in this case, is being degraded per bacterium. This is normalized per bacterium. So this is what I call the metabolic flux. How quickly is a bacterium processing this pollutant? And these are different strains that harbor different catabolic pathways. And the main point here is that even a little bit of ethanol, tiny little bit, has a severe inhibitory effect per bacterium on the degradation of toluene. That's without ethanol and with ethanol, a significant decrease. And that's probably because ethanol, unlike BTEX compounds that they get degraded by so-called inducible enzymes that are only produced when needed, ethanol gets degraded by constitutive enzymes through central catabolic pathways like Krebs cycles. And their presence results in this preferential degradation, and it distracts the biochemical machinery from degrading toluene. To understand the basis of that better, we use what we call bioreporter strains. These are bacteria that are genetically engineered to shine when they are induced. What happens is that we insert a reporter gene, in this case LOX, right next to the catabolic gene. This is the gene that codes for the enzyme that degrades BTX. Remember, what genes do is they code for enzymes or for proteins. That's the only thing that genes do. That's what they're for. And the TOL gene codes for toluene dioxygenase, which is the enzyme that attacks the BTX compounds. When this gene is expressed, so is this one that codes for luciferase, and the bacteria shines, as you can see here. And you can measure that light production using a luminometer and use that information to infer the level of induction of the bacterium. So using that approach, we see that when we increase the concentration of ethanol, both the metabolic flux and the level of gene expression decrease. So to me, this is evidence of what is known as catabolite repression, which is a mechanism that cells use to save energy that would be associated with making enzymes that are not needed when they're feeding on ethanol. Now, so this is a negative effect per microbe basis. But keep in mind also that ethanol is like candy to microorganisms. They love eating it, and when they eat it, they grow. And the more organisms that grow, the more workers that you have that can attack your pollutants. And that's illustrated in this data. Now we're talking about benzene. This is the amount of benzene that comes into the reactor. This is what comes out. The difference is what is degraded. The amount degraded increases significantly when we add a little bit of ethanol. Why? Because now we have more bacteria. So what I'm trying to tell you is that 3 bacteria working at 50% capacity are still faster and better than 1 bacterium working at 100% capacity. And that's sort of what we're seeing here. That overall it could have, on the overall population, a positive effect on degradation if you had unlimited supply of oxygen or unlimited supply of of nutrients. The problem is, so what I'm saying is that the inhibitory effect of ethanol on specific degradation activity issues like catabolite repression or the dilution of the metabolic flux can be offset by additional cell growth. But the problem is that you have so much ethanol, I mean, typically 4,000 or 5,000 milligrams per liter are going to be left in that plume versus 1 milligram per liter of BTX. The ethanol is going to exert such a high oxygen demand that it's going to very quickly drive the system anaerobic, and under anaerobic conditions, the hydrocarbons just do not degrade well. And that might hinder the natural attenuation of BTX. To illustrate that, I'm going to show you some data that we do with columns, now moving to a larger scale. These are flow-through columns that are being fed contaminated groundwater, and they have sampling ports so that we can take concentration profiles. And you can see that when we compare the impacts of MTBE versus ethanol, here, in this column with MTBE, the benzene is degraded very rapidly, within the first few inches. Why? Because it's easy to degrade. Bacteria that degrade benzene aerobically are ubiquitous. You probably have some under your nails right now. And the MTBE, unfortunately, is not degraded. It's very recalcitrant, this compound. In contrast, in the column that receives ethanol and BTX, here it is ethanol, the one that is preferentially utilized, and its degradation consumes all of the oxygen, all of the sulfate, all of the nitrates, all of the nutrients and electron acceptors that would otherwise have been available to support BTX degradation. And as a result, benzene, which is recalcitrant under anaerobic conditions, persists. So, regarding the geochemical footprint of ethanol, we see that the electron acceptor demand that it exerts is so high that it drops the oxidation potential to levels characteristic of methanogenic conditions, and methane begins to accumulate. Whether that can pose an explosion hazard or not, I don't know. I suspect not, but in some cases, that's something to consider. We also see that acetate or vinegar, which is a product of anaerobic ethanol degradation, begins to build up, and that causes the pH to decrease. So low pH is a concern. It may mean solubilization of heavy metals. In this case, it may mean inhibitory effects on bacteria. Here, the pH drop was small because this system was very highly buffered. We had 1,000 milligrams per liter alkalinity artificially added, but a poorly buffered system may experience a more pronounced souring effect. Now, as to what it does to the microbial community structure, Well, to do that, we use a technique called denaturing gradient gel electrophoresis. It's rather simple. What you do is you extract the DNA from the bacteria, and you pass the DNA through a gel under an electrophoretic gradient. And the idea is to separate the DNA from different bacteria into different bands. So you get a spectrum of different bands, each of which represents a bacterium. And you can cut that band, and using sequencers, you can determine the sequence and go to a database in a computer and identify who is there. Now, that doesn't tell you what they're doing, but knowing who they are is a step in the right direction. So using this approach, we see that we're comparing data here for a column where the BTEX compounds are alone, or with BTEX, or with ethanol. When the BTEX compounds are alone, we see a lot of bacteria that are highlighted here in yellow. These are bacteria that are known to degrade toluene under anaerobic conditions. And there's more of them, or at least a higher abundance of them, than in the column where there is ethanol. Because although ethanol promotes the growth of bacteria, most of the bacteria that grow on ethanol are incompetent. They are not necessarily the key players that you want to degrade the hydrocarbons for you. So that's what I call genotypic dilution. You still have more degraders, specific degraders, but as a percentage of the overall population, they're less. So that's genotypic dilution. So what does this all mean? What that means is probably that when you have a spill of ethanol containing BTX, you're going to have very rapidly an anaerobic zone where there's going to be very little degradation of BTX, and then due to some negative effects such as metabolic flux dilution and catabolite repression, degradation is going to also be hindered, and that may result in longer plumes. But the question is that effect, the plume elongation effect, significant? Significant both from the point of view of statistics, but also significant from the point of view of public health. Is that going to make the plume now reach receptors that would otherwise be safe before you added ethanol? The only way to answer that question is to go to the field and to try to obtain data from contaminated sites. And based on monitoring wells, then you contour the data and you define the plumes. And I have no idea who this guy is. But anyways, we did that. We call that the plumathon, right? And the idea of a plumathon is that you obtain a bunch of data and you take an epidemiological approach to answer that question. Is the elongation effect significant or not? So we obtained data from 2 states. I used to live in Iowa at that time. And we obtained data from about 218 sites that had a very low probability of having ethanol. We selected sites where they had never used gasohol. Hard to find, but we did. And then the Kansas Department of Health gave us data for sites that did contain ethanol. And we compared the two. I have to acknowledge that there are many factors besides the presence of ethanol that can influence the plume length, like the amount released, the permeability of the site, the age of the release. But it's not different than what epidemiologists face when they try to establish a link between, for example, cigarette smoking and cancer. You can always argue that maybe genetics plays a confounding factor, or maybe it is your diet or your lifestyle, or how many times you laugh in a day maybe is more important. But the point is that how do they deal with that? There's only one way. You take a sufficiently large data sample so that you randomize these confounding effects. And that's what we try to do to try to get a converging lines of evidence. So what we did find is that the benzene plumes with ethanol were longer. The difference was statistically significant. But I am not sure that adding 80 feet to the length of a plume means much to public health. Frankly, most regulations demand that your drinking water well should be at least a quarter mile away from a gasoline station. So really, this is 80 feet is not that big of a deal. The effect was also observed, but not statistically significant for toluene, because toluene degrades easier under the anaerobic conditions that are exacerbated by the presence of ethanol. Just before, I want to show you, finally, at the largest scale, some field study that we conducted here in the Ilha da Magia, the magic island of Florianopolis in Brazil. We had to go there because they wouldn't let us spill stuff here in the US. So anyways, the idea with a friend of mine, Henry Corsail, sponsored by Petrobras, Henry did most of this work. The idea was to dig a hole and right at the water table, release 100 liters of Brazilian gasoline that contains 24% ethanol. The site is very well monitored with many well clusters. And what I'm going to show you is first the migration of the tracer of the water. You can see that the number of days that have passed over here. It's a multi-year study. After a couple of years, we see these plumes typically tend to be like cigar shaped. The reason why this is a little bit broad is because it's under the influence of some tidal action here, and also the gradient was very flat. But anyways, you can see that we're capturing the plume as intended. When we look at the migration of ethanol, it does begin to expand along the same direction, but then it begins to retract. Remember what I told you about natural attenuation? There's a point at which the attenuation rate becomes greater, and then it's gone in less than 3 years. The maximum extension that it reached was about 15 meters, 50 feet or so. Now, just because ethanol is gone doesn't mean that its impact or influence is gone. It has left behind an anaerobic shadow. Maybe there is acetate. We did detect some acetate and so on. So there's still, this zone is not that optimal for biodegradation. But when we look at the BTEX plume, I want you to keep an eye on the green, which is benzene. Benzene begins to leave the plume because it's more soluble than the other hydrocarbons, and it's also more recalcitrant under the anaerobic conditions that ethanol just created. So this is when we went, oops, it wasn't supposed to go that far. But fortunately, at the last sampling event, it's coming back, indicating that definitely natural attenuation can take care of ethanol gasohol spills. My concern there is that natural attenuation is sometimes overprescribed because it is much cheaper than more aggressive remediation techniques. And if you overprescribe it at the wrong place, it may create some negative publicity and a bandwagon effect that may hinder the application of this. But anyways, to wrap it up, this is some of the conclusions that we summarize in a paper that we published, a feature article in ES&T a while ago. Ethanol definitely can hinder the natural attenuation of benzene, which could result in longer plumes, and of course that means higher risk of exposure, but the significance of this effect is going to be site-specific depending on the release scenario and the assimilative capacity of the aquifer. But the take-home message I want to leave you with is that I do believe that it is important to try to formulate gasoline in a manner that minimizes air pollution. And if given the choice between MTBE and ethanol, I would have to conclude that the impacts associated with the use of ethanol are more manageable and of shorter duration and less significant than those associated with the use of MTBE. Thank you for your attention.
Great. Do you have any questions?
Yeah. Thank you very much. Fascinating presentation. I learned a lot. Two things. One observation. The aldehyde measured in a tunnel in Sao Paulo were higher than the norm, but below the WHO recommendations. But the question I have is, are you aware of, have you conducted studies of this nature with respect to ETBE?
It's an excellent question. No, and the reason is, as you know, MTBE accounted for 85% of the oxygenate market, so we focus on MTBE. But ETBE is another thing that the American Petroleum Institute, who funded part of this work, was interested in us looking at. And I think that it will probably be similar because it is an ether, but it will probably be easier to degrade than MTBE, because you can always have that little chain that can be beta oxidized. So I would expect to be a little bit more degradable, but yet still recalcitrant.
Okay. Oh, one more.
I have a question on a related subject, not exactly the subject of your talk, but we have been trying for decades to develop microbes that can be injected into reservoir and change the grades of oil, separate oil and gas. Mm-hmm. And so far we have failed, primarily because there are resident microbes in the reservoir. Yeah. And when we send the laboratory developed microbes into the reservoir, they say, oh great, free lunch, send me more. Because they've been there for tens of millions of years, and they own the real estate. since you are in that area,
Yes.
what is your view about the likelihood of us developing robust enough microbes?
Sure. Yeah, what you're talking about is called bioaugmentation. It's an area that was discredited in the 1980s by many snake oil salesmen that were selling things, that weren't needed because there were already indigenous organisms doing the job. And if they weren't doing it, it's not because they weren't better predisposed genetically or physiologically, but because perhaps they were lacking a key ingredient, or the substrate was not bioavailable, or they were just trying to do something against thermodynamic laws, like oxidize and a chlorinated compound. But it does work. It has gained a lot of notoriety lately, provided that the metabolic niche that you're trying to address is not being filled already by the indigenous community. And where I see a great potential is in injecting shales, that have this residual oil with methanogenic bacteria, to convert that, unusable or unextractable oil into methane and CO2. The CO2 is going to probably help the mobilization and extractability of that oil. And more importantly, you're going to have a more movable form of fuel, methane, being like a natural gas. I think that we didn't think that could happen sufficiently fast. We thought that would take geologic ages to see any significant conversion. But there's been a lot of recent data that I have been seeing that suggests that it might be something worth considering.
Okay, great. Well, I'm going to ask now Sue Powers to come and give the final talk for this session. And she is from the Coulter School of Engineering at Clarkson University, and her talk will be on the life cycle analysis.
Thanks, Amy. And as you might have heard, I've worked very closely with Pedro in the past. We worked for the state of California looking at groundwater problems with ethanol. In the state of California, when they had MTBE problems, they thought they were going to be innovative and look at groundwater problems with ethanol. Ethanol was defined as their future. They were not interested in any other problems. They were now aware of groundwater issues because that was the problem with MTBE. They didn't care what happened in the Midwest because of the increased farming. They didn't care what happened globally because of carbon dioxide. And that work for the state of California really opened my eyes that we really had to use a broader life cycle perspective. So that started me on my quest to do what I'm doing now. So we all know we're looking predominantly, I'm going to be talking about corn, soybean rotations, so only dedicated feedstocks here. In addition to biodiesel from the soy and ethanol from the corn, we can also make ethanol from the corn stover, which is a cellulosic fuel and is the focus of a lot of things. So for our life cycle perspective, mostly what we want and we're talking about is we need new fuel for our super big vehicles, which I notice there are a lot of in Texas, more than I'm ever used to seeing. But in reality, we've got to look at this whole life cycle. You just can't worry about what happens down here and fuel spills and things like that. Luckily, with these feedstocks, we get a lot of byproducts. Those byproducts give us a lot of extra value, both economically, but they also mean that if there are environmental impacts throughout this life cycle, we can allocate some of those impacts to these byproducts. It's not necessarily just the biodiesel and ethanol who are consuming all the energy and things. It's also these things. I also want to point out that there's a lot of food left after the fuel is taken out. So partly mitigates the food for fuel analysis. At least all the protein remains in those byproducts. So let's look at what some of these environmental impacts are. So at the first stage, the feedstock production stage, we have all sorts of water problems, air emissions largely from the energy that's consumed, but also from the nutrients and other things. But our life cycle doesn't start there. We're adding to our farm lots of energy, fertilizers and pesticides and environmental systems. And there's also energy and raw materials that were used to make those components. And so our life cycle here doesn't start at the farm, but it has to continue the upstream aspects as well. Downstream of the farm, we have our processing and fuel use. We have a lot of energy and other raw materials that go into the processing, Fuel spills, as Pedro was just talking about, predominantly here, although there's also some at the ethanol production facility. And we have the same environmental releases to the atmosphere, predominantly the same environmental releases to the atmosphere. So a life cycle assessment, what I'm going to be talking about, is sort of a thorough analysis of the mass and energy flows throughout that life cycle, all the way upstream of how we made the energy and how we made the fertilizer, all the way through the use. So once you do that mass and energy analysis, you have to aggregate and collect. Different species can contribute to the same environmental impact. So you have to figure out how do you add those together, and there are special ways to add those together. And then the real reason that we do this is it's a decision-making tool to understand what do we do to move forward and make decisions about what our choices are in feedstock. So if I look at corn and soy and stover, how do we sort out what are the environmental impacts of those different things? I'm going to be talking about, this is a week's worth of seminar for you. I'm going to talk just about a couple of impacts, and mostly I'm going to be talking about these stages of the life cycle assessment, one aspect with the energy, the biofuel processing also. So my goal today is to give you some understanding of some of the numbers that you've seen, the net energy value of ethanol and things like that. Where did these numbers come from? The reason I want to do is to look at broader questions. So for example, we've talked about energy security, energy conservation, environmental quality. I was most interested in soil water quality. A lot of people are focused on emissions because that's what happens mostly at the tailpipe. But all of these other environmental impacts also happen upstream in the life cycle. So particularly, I'm going to be talking about nitrogen versus carbon and energy. So I'm going to break this into two parts, the energy part and then the nutrient and carbon part. So energy use, we've seen this earlier today. The reason that biofuels are so good is because most of our energy is, quote, free energy from the sun through photosynthesis. When we look at energy analyses, we usually don't count that energy unless we're truly doing a thermodynamic energy balance. It's not usable energy to us in that sense. So that's our free energy in. We have a lot of other energy required for the processing. And so we have to figure out how do we add up all those energy sources and how do we make sense of that from an energy security and an energy conservation standpoint. The most standard metric used for energy is the net energy value, which is defined as the energy value that you get out with the ethanol or biodiesel that you produce, minus what I define as the consumer energy in. We're not going to count the solar energy, but you do want to count energy that could be used elsewhere. So that's the net energy value. And there's a lot of discussions about this, and it's really not a great metric because it lumps everything together. You lose all the details that we really want to get out of this analysis. So if our federal government tells us right now our national energy policies or energy security, then we really need to know how much of that energy input is domestic versus foreign. So we really want to get at that. And we also, energy conservation, how much of it is renewable? And if this country, we really cared about global warming, it's not necessarily part of our national energy policy, but we'd also want to know what percentage of that overall energy in comes from fossil fuel. But what's really important is that we quantify all of these over the life cycle, because otherwise we lose some important contributions. Now this is a plot of reported corn ethanol NEVs. We saw this in a little bit different form this morning. So BTUs per gallon is our calculated ethanol net energy value, and this is time. And you can see early, we weren't doing very well. Our processes on the farm and the ethanol production facilities were not very effective, and so NEVs were all very negative when we first started making ethanol. Over time, though, a lot of people started, and this is many different authors, started to report positive net energy values, averaging somewhere around 20,000 BTUs per gallon, but the scatter was pretty much very significant. I just want to point out that a lot of the scatter is predominantly from one reference. Pimentel and Associates continue to predict very negative NEVs, whereas this is many different authors. And so if you say, well, they are doing both their calculations different and they're using other data. Some of the data used is the same sort of data that was used earlier on. So in general, it looks like there is a growing trend of NEV, and I do believe personally that the net energy value is up in here. This was the Science article from last January, so that was the most recent, almost 20,000 NEV. But again, that doesn't help us understand energy related to our national priorities. So, sorry, one more slide on net energy value. Stover does do better than corn, about 50% better, because the allocation of the energy between the stover and the corn helps the stover a lot. So what we really need to do is to go back to the raw data and figure out how to count it so we can separate the renewable, the imported, and the fossil fuel. And so that really requires to go back and calculate. This is an example for natural gas for corn. Some of the natural gas goes into the corn farm. A lot of it goes into the ethanol process. We call these the direct inputs. But we also have all these upstream inputs, which are very important for natural gas. That's what's going into predominantly to making nitrogen fertilizer that we need for the corn production. Some of it also goes into electricity and fuel, which then also come back into our process. But electricity is an energy carrier. You can't count that as part of your life cycle assessment. It's not a primary energy source. So by doing this, and we use some data by Michael Wang and the GREET model from Argonne National Lab, we had to do a lot of work to break that model down to get at the data. But if we do that for all of our energy sources, you can come up with a real good understanding of energy use for corn versus stover. So here I have the three primary direct parts of our life cycle: what's used on the farm, transportation, and processing for corn versus the same thing for stover. And I can point out a couple of things directly. There's a lot more use. This is farm and upstream of the farm. A lot more for corn versus stover. The processing, stover takes a lot to process, but this big yellow bar is biomass energy. Almost all of it is the recovery of lignin and syrups from what's left over from the corn stover is put back and is burned to make heat and power. Corn, that same material, is used as a food, so it still has very good importance, but not for energy value. I want to point out that what we've quantified here, these are the upstream energy. So this is what it takes to create chemicals, to create electricity, and to create the fuels. We can further break that down. And this upstream energy for the chemical is mostly that natural gas. The red is natural gas used to make the nitrogen. So by doing this level analysis and breaking it down at this level, we can really start to understand how our energy used for these primary energy sources, so we can categorize them into what's really important. So if we compare, this is corn again versus stover, there's less total energy used for the stover, a lot more of it's renewable, but there is still some petroleum and fossil fuels that are used. But it's looking much different than the corn ethanol. So just to summarize the energy part, lower NEVs for stover, many more use of renewable energy because we're burning that lignin and syrups, and it also uses much less imported oil. And so there are some real benefits to stover versus corn from an energy standpoint. Now, if we switch gears and say, well, what about the nitrogen? And so I just picked out a couple of environmental impacts here because I couldn't cover them all today. So our goal here is to really look at the environmental impacts with agricultural activities. And it says corn and corn stover, but I'm really going to talk about corn and soy for this part of the talk. And I'm just going to look at greenhouse gas emissions versus eutrophication. And so we've got this carbon versus nitrogen issue that somebody alluded to this morning. So nitrogen is necessary for all living things. What we do is we take inactive nitrogen, N2, out of the atmosphere. We make it into very active nitrogen, nitrates, and ammonia. The result of that has been substantial increases in corn and soy, mostly corn yields. But the problem is that excess reactive nitrogen is very much responsible for environmental degradation. And so we get all sorts of environmental impacts. I'm going to just focus on these two. So nutrients in water, this is what eutrophication is. If you put too many nutrients into water, algae is happy, it grows productively, water plants grow productively, they're wonderfully happy, but the aesthetics of your lake water is a lot different, and you have algal blooms. And there's also problems with mutations from excess nutrients. But it's not just a problem at that local scale. That was non-point solution right there. At a national scale, we have a bigger problem called hypoxia, which you've probably heard of in this part of the world, which is the extreme case of eutrophication. And so much algae and so many plants have grown, when they die, they consume all the oxygen. All of a sudden, we have an anaerobic system. This has happened at the end of the Mississippi River. There's an area off the coast of Louisiana that's about the size of Massachusetts. It's ecologically dead. Big fish and big things have moved away, but all the little things just couldn't get away, and they have died. And so this is a real extreme ecosystem tragedy. It's resulted in changes in the fisheries and the economy of the region. So it's a real, true environmental impact of national scale. So those are the issues. Now let's look at trying to quantify some of these. Our carbon cycling, again, just like the sun, we have free carbon is taken up by the plants, again, through photosynthesis. And at the same time, we have carbon emitted during fuel combustion. Some people think that this equals that, so it's a net neutral carbon cycle, but in reality, we also are consuming a lot of fossil fuels during the process. They contribute to global warming. We have methane and carbon dioxide released from our upstream processes, particularly methane in making nitrogen fertilizer. And so they were all contributing to the carbon cycle. So if we summarize those environmental impacts, we got a real benefits of our corn, soy, and stover system. Greenhouse gases are reduced compared to petroleum. Fossil fuel depletion is reduced compared to petroleum, but at the same time, we have some negatives. We might be damaging the organic content in soil and soil erosion. And we also have all of the nitrogen-related impacts, our detriments, nutrients in groundwater, acidification, and greenhouse gases. So we end up with this environmental benefits that are largely related to the carbon cycling compared to the environmental detriments that are largely related to the nitrogen cycling. And how do we balance these positives and negatives? So I did some work when I did a sabbatical at NREL, looking particularly at soil and water systems in the eastern half of the United States. I was very interested in this hypoxia and the eutrophication issues. So for these 4 major watersheds in eastern Iowa, there was data about how much nutrients were discharged to the Mississippi River. And so the hypoxia is predominantly related to corn, soy farming in the Midwest. That is the number one reason for that hypoxia zone. And so I really wanted to get at that from here. And about 64% of the land mass in this area is row crop. So the nitrogen cycle is a lot more complicated than carbon cycle, and I'll try and show this to you quickly. This is what we want to happen. We apply fertilizer nitrogen, often in the form of ammonia. It's nitrified to make nitrate. Both ammonia and nitrate are taken up by the plants to make nice, big, green, healthy plants that we can harvest and get our food, our feed, and our energy. That's what should happen. But at the same time, we lose some of that nitrogen through mineralization and immobilization. It ends up in the soil system. We have additional nitrogen inputs, especially with the soy and nitrogen fixation and atmospheric deposition. And so all of these aspects contribute to our ability to quantify the mass and energy flows through the system. And that's what we want to do in a life cycle. So we have to quantify all these flows. Here are discharges predominantly of soluble nitrate to groundwater through tile drains and base flow to rivers in the Gulf of Mexico. We have soil erosion that's also ending up in the river. We have volatilization of ammonia. And ultimately what happens is we have denitrification, and all of the nitrate that caused problems in our aqueous systems ends up getting denitrified back predominantly to nitrogen, but we have nitrous oxide and N2O and NO released to the atmosphere as byproducts. So all of that's happening at the same time. If we want to do a mass and energy flows for a life cycle assessment, we have to try to quantify all of these mass flows. That's a lot of work. And I focused on what I'm going to show you predominantly is what's happening here. Although you have to quantify everything else in order to figure out what's happening there. So all those nutrients that are coming off of those corn and soy fields are ending up in the Mississippi River and the Gulf of Mexico. This is the total nitrogen load to the Mississippi River from those three watersheds in eastern Iowa. This is over time, and this is National Ambient Water Quality data. You can see a huge change, several orders of magnitude differences in the total nitrogen load to the Mississippi River. And when we're down here, we have very little nitrogen, not much hypoxia. When you're up here, you've got huge hypoxia problems when there are large loads. The reason that we have all this variability is these years were drought years. There wasn't much rainfall to carry the nitrogen. This was a flood year. There was a lot of rain to carry that nitrogen. If you look at a standard LCA practice, including what's done in the GREET model, they use a fraction of the fertilizer. That's what they come up with. It's a great average. It's a perfect average. But the environmental impacts happen at these extremes. If we really want to understand environmental impacts, we can't count on the averages. So the model that we came up with that was a simple linear relationship with rainfall did a pretty good job of capturing some of the ups and downs and therefore some of the variable environmental impacts. So that had to be done for all of these different sources and sinks. These are all sinks of nitrogen. Most of the nitrogen does end up in the plant matter. There was one year, that the flood year, that there's a lot of denitrification. Our wet and dry years both had very low corn yields and soy yields, but very different nutrient runoff yields. And so what we do is we take all that information and we calculate how much eutrophication do we expect. And so eutrophication, now we're going to put it in a eutrophication potential. That's like the global warming potential, and it enables us to add the components of different things. And in this case, we added up total nitrogen and total phosphorus. Phosphorus is a much more potent eutrophication contributor. So even though there's not much phosphorus that gets into the water, it's more potent because the cells are limited by phosphorus differently than they are. So what we can see is that corn contributed the most, just a little bit from soy, a little bit more of the phosphorus from soy, and the nitrogen contributes far more than the phosphorus to the total. So overall, you can see here that corn, and mostly because of the high nutrient requirements for corn, almost all of our eutrophication, and therefore hypoxia in the Gulf of Mexico, we can contribute to the corn. Those were average values. I just told you the averages were not that meaningful. We really need to think about these variable because that's what contributes to the these extremes and hypoxia. And so now this is what's discharged from the eastern Iowa watersheds. And so this was the model I just showed you in comparison with the real data. That's what the model says for our corn soybean fields. We can compare that to the predicted, what it would be like if it was background without the corn soy farm. Huge difference, orders of magnitude. So that's one benchmark for comparison to see how important this is. If you looked at the national water quality standards, this is what they say the maximum total eutrophication potential should be. We are still factor of 2 in many cases, twice as much nutrients into the water than we would want from the water quality standard. And there was a task force that looked at hypoxia, and they said if we could maintain this as our eutrophication potential, the hypoxia problem would be a lot less. And you can see, actually on average, this isn't bad, but it's those years where we have the extreme cases that we're going to be contributing substantially to hypoxia. So the eutrophication and the hypoxia issues, I think, are very important water quality issues that we need to be concerned with our biomass and bioenergy. Greenhouse gas emissions, you've already seen. The carbon cycling, now we have to add that there's a lot of N2O released. When we put nutrients on the field, they biodegrade into nitrification, denitrification. N2O is a side product. So if we add all those up, I'm only looking at this part, so I'm discounting this from my life cycle, just so I can show it all to you. We can see the global warming potential. And we have 3 contributors to global warming here: carbon dioxide, mostly from fossil fuels, nitrous oxide, and methane. The blue is direct use from corn. The red is directly from soy, so this is at the farm and the transportation and the upstream. This is a real big one, mostly from, this is the manufacture of nitrogen fertilizer releases both a lot of carbon dioxide and methane. A lot of methane is used to manufacture nitrogen fertilizer. And it's really important to see if we did not count this negative from the nitrogen cycle, the N2O, we would grossly underpredict our overall global warming. So we have a large amount of the global warming is from the farm, but there's also a lot of these upstream processes that are very important that we can't neglect. And that's what, by doing a life cycle assessment, you incorporate those upstream processes as well. And again, it's predominantly from the manufacture of nitrogen fertilizer. So if we summarize and compare 2 different things here, carbon versus nitrogen, there are a lot of benefits to the carbon cycle because of using biomass fuel, and I think that we all agree to that. Carbon uptake, sequestration, we're not bringing carbon out of the ground and burning it, we're recycling it in our atmosphere. But we got to balance this with the detriments from the nitrogen-related impacts. Eutrophication and hypoxia are significant problems in the Midwest. It's not impacting California when California wants to have increased ethanol, but it is having a big impact in the Midwest. And we also have to remember that N2O is a significant contributor to greenhouse gases and associated with this, and we don't want to neglect those in our calculations of greenhouse gases. So we've got this fundamental trade-off. We've got the more local and regional impacts of the nitrogen versus the global impacts, benefits of the greenhouse gases. And I can't tell you how to balance those, but those are things that we don't want to neglect. And if we look at the corn versus soy discussion here, corn, because it has such high requirements for nutrients, causes a lot of these problems. There's a greater overall energy use and much greater impact from corn than soy, and that's also true from stover, because stover sometimes is considered a waste product, so most of that energy and nutrient use gets allocated to the corn, not to the stover. So I've talked about a few different perspectives, some energy-related perspectives and some soil and water quality-related perspectives. And based on this, I think that we really want to think carefully about substantially increasing the amount of use of corn as a feedstock because of the detrimental impacts of corn on our environment. But I did consider all of the issues. There are many other environmental impacts that we would really want to understand to do this thoroughly, and that's a whole nother week, so I won't go there. Thank you very much.
Okay, do we have some questions for Susan?
First, I would like to congratulate Susan. Very nice presentation. In fact, the questions would also take a week, as you know.
Yeah.
So I'm going to limit myself. I have one observation. In your view graph on the ethanol refinery, I noticed that you use something like less than 4 megajoules per liter of ethanol of fossil fuel, while the written guarantees from the manufacturers say something like 12 megajoules per liter. That's your 34,000 BTUs per gallon. And I was wondering, my question is, how did you discount that down to 4?
We used, and we place a lot of value on the data that's used by Michael Wang in the Greek.
I understand, but
So,
how do you reconcile the two?
for the same reasons that he reconciles it. So I am using his justification. I'm not an expert in ethanol manufacturing, and so I have to rely on other people's expertise, and that is the expertise that I relied on, and actually my graduate student Amanda Levine relied
I would like
on
to
that.
point out that that's not entirely a safe estimate there.
I agree, and there's a lot of, and that's why I think the numbers go all over the place.
Therefore, my second comment and question is, you see, science is not democratic. Both sides cannot be wrong, right or wrong, right? Either one is right and the other one is wrong, or the other way around. we cannot vote on science. So
That's true.
voting doesn't cut
Right.
here. So I think it would be very nice if we kind of arrived at a common picture and delineated very carefully, not just saying, oh, they use old data, or they do this, or maybe they use a different metric, but we kind of pointed out, point by point, where are the differences, and then sum them up. And I think that, I did some of it 3 years ago in my big paper that nobody quotes because it's too long and also not very convenient. But that needs to be done, and that needs to be gotten into the public domain.
Can I just
Yes.
add? So I don't necessarily agree that there's a right and a wrong. There are
Yeah.
different approaches that lead to different numbers.
Okay.
And I think that's okay. It doesn't mean that one's right or wrong, it's different approaches. And I agree with you that we have to so the analyses have to be very transparent.
Yeah.
If we want to be able to do what you just said, anyone who does a life cycle assessment needs to very clearly identify all of their assumptions and where did the data come from. And that's generally not done well in life cycle assessments.
That's right.
Not just Pimentel's and yours, but everybody's.
Right.
And so we have tried, and others, Michael Wang has tried, and I think the Science article that was published in January of this year, and a lot of the rebuttal literature that was published there, have pinpointed some very specific.
Oh, yes, they have.
But I think that they've done a good job of pinpointing some very specific reasons, and some of its differences in data, some of its difference in the boundary of the life cycle, and that's really a big one.
Right.
What do you include or what don't you include in the boundary of this life cycle?
Well, I think we're going to come back to that tomorrow, so
okay.
let's put that outside the framework now. Anybody else? Okay, well, I'm going to move us to our last session. Thanks very much, Susan. I'm going to move us to our last session, which is to talk about the politics of biofuels in the United States. We're very fortunate to have two really good experts in this area. Margaret Kriz is a correspondent with the National Journal and has been covering the Hill for 20 years. Okay, so she knows that in and out. And then after her, we'll have Gal Luft, who's the executive director of the Institute for Analysis of Global Security.
Hi, you will notice I'm the only one that doesn't have a PowerPoint presentation. So here it is. This is the National Journal. I was thinking of putting it up on the chair. You could look at that instead of looking at me, but we'll leave it right here. That's a publication I work for. It's Washington Politics and Policy, a weekly news magazine. I've been writing there for 20 years and covering energy and environment. Today we heard about the need for perhaps the best possible government policy on ethanol or development of biofuels, but I'm about to talk about the reality. When it comes to Washington, ethanol, or I guess I should say biofuels here, have the potential to please almost everyone. Farmers love it, so those 20 senators from farm states who usually vote for ag issues are going to also vote for any kind of pro-ethanol legislation coming up in the next couple years. Environmentalists are warming to ethanol as well, because in theory, they reduce greenhouse gas emissions, although we can talk about that. And so it's good for global warming, and it replaces big bad oil. Ethanol is supported by all the presidential candidates who are going to Iowa in the last summer, 18 months before the Iowa caucuses have begun. And polls show that the American public is big on renewable energy, including ethanol. But some Washington pundits predict that ethanol is just the latest craze in energy policy, like hydrogen and fuel cells, stuff that people expect immediate gratification from and they're not getting it. So they say that ethanol will be king only as long as it gets huge subsidies and only as long as gasoline prices remain high. Some pro-market Republicans and lawmakers with more sympathetic view on the oil industry are not crazy about all of the ethanol mandates that are being tossed around Capitol Hill these days. So if you look at it that way, the question is, how long will ethanol's honeymoon last in Washington? And what is going to pass during these golden days? You all recall the President Bush's last State of the Union address, which we heard about this morning, so I'll skip over that part. But ethanol has become an issue in the November congressional election. Around the country, ethanol has been featured in political campaign ads running for the House and Senate cases. And my favorite one has been Missouri Senator Jim Talent, who's running for re-election. He's calling himself Mr. Ethanol. Every time I hear that, I think of Mr. Potato Head. Talent's competitor, Claire McCaskill, unearthed the fact that 15 years ago, when Talent was a state senator, he voted against the creation of a state ethanol fund. She's been hammering him with that fact ever since. Then there are the presidential candidates, or the folks that are just testing the waters. They're already tripping over themselves for FaceTime in Iowa. One of the most popular things for the candidates to do this summer, besides go to the Iowa State Fair, was tour an ethanol plant. Great photo op. They ought to sell tickets. They'd be making a whole lot of money if the ethanol makers charged those guys to come through. McCain toured a plant when he was there. Arkansas Governor Mike Huckabee, who's considering a run for president, took a stroll around a plant in Iowa Falls. Now, Hillary has announced that she wants to require half of all gas stations in the nation to carry flex fuel pumps within the next decade and have it in all of the gas stations by 2025. Joe Biden and George Allen have also said nice things about ethanol. Now, McCain is an interesting case because he didn't run in the 2000 primaries, the Iowa caucuses, because of his position on ethanol. He does not like ethanol subsidies. This summer, when he was at the Iowa State Fair, one of my colleagues was following him around, Jim Barnes, and he told Jim that he doesn't support ethanol, he does support ethanol as a way to reduce greenhouse gases and to reduce Americans' dependence on foreign oil, but he still doesn't like farm subsidies, so that might come back and bite him. But the presidential race is a ways off. We won't hear about that until at least the day after the midterm elections. So what about next year? What will Congress do to boost biofuels? Well, some of that depends on whether the Democrats or the Republicans are in charge in the Senate and the House. Last year's energy bill, which was Republican-led, was ethanol-friendly. It provided $2 billion for biofuel development. It also mandated an annual use of 7.5 billion gallons of ethanol and biomass by 2012. And we heard today that we've already blown past that number. The Republicans have been really big on emphasizing technology development. In fact, Senator Pete Domenici, who chairs the Senate Energy and Natural Resources Committee, is bullish on having Sandia and Los Alamos National Laboratories conduct research on cellulosic ethanol. And I don't suppose that has anything to do with the fact that both of those laboratories are in his home state. But at least he's a lot less keen on mandates to support ethanol. Democrats, who are straining at the bit to regain control in the House and the Senate, have a cornucopia of bills to support biofuels. I mean, they would do all kinds of things, and they're already starting to put out the information about their legislation because they want to spread the gospel of ethanol. 3 kinds of legislation are possible: bills to encourage the growth of new crops or new technologies to make biofuels, bills to pave the way for a distribution of ethanol at the gas pump, bills that encourage sales of more cars that ride on E85. Now, each of these types of bills could end up in different committees in the House and the Senate. Depends a lot on how they're phrased. So if they phrase a bill, oh, I want this bill so that it's going to clean up the air, well, it's going to go in the Environment Committee. If they say, I want to support the growth of certain crops that will help with biofuels, could end up in the Ag Committee. If they say something straight on energy, we want to help the Americans' position on energy, could up in the Energy Committee. So what I'm saying here is that the jurisdictional disputes could be pretty strong, and that could slow down anything happening in the next year. As far as increasing the supply of ethanol, there's 2 ways of handling it. We heard a little bit about one of them. We can either import it or you can make it in the U.S. At one point this year, when the gasoline pump prices climbed beyond $3 a gallon, President Bush and some of the GOP officials in the Congress wanted to lift the 54-cent a gallon tariff on imported ethanol, most of which they expect would come from Brazil. But the farmers worried that the Brazilian ethanol would flood the market and lower the price they get for corn. So, not surprisingly, some corn state Republicans, most notably Dennis Hastert, who's from Illinois, stopped this. So what happens if the Democrats win in the House? Well, the Democrats have been blaming the Republicans for the price of gasoline this year. So if they win in Congress, either the House or the Senate, you can imagine that they'll try come through on some of their promises. But it will be hard, because no matter who wins, Democrat or Republican, they won't win by a very large majority. So they will have no big mandate, and I question whether they'll be able to pass anything in the way of an ambitious legislative package. Democrats are promising to invest heavily in energy resources in rural areas. It's a strategy designed to appeal to so-called red state voters. But I want to just kind of go over a couple of different pieces of legislation that have been proposed by the Democrats so far. You've got House Minority Leader Nancy Pelosi and other Democrats who formed something called the Rural Working Group, and they outlined their own agenda for ethanol this year. They want to double the percentage of biofuels sold in the United States in the next 6 years. They want to require 75% of all new vehicles sold in the next 7 years to be flex fuel cars. Imagine that, 75% in the next 7 years. They want to push more cellulosic ethanol research and expand the number of corner gas stations that sell E85. On the other hand, you also have John Dingell, who's a Democrat from Michigan. And if the Democrats win, he would be reinstated as the chairman of the Energy and Commerce Committee in the House. He and Democratic Whip Steny Hoyer of Maryland have proposed a Manhattan Project type of research program that would, among other things, build a national infrastructure to distribute ethanol around the nation. On the Senate side, in July, 40 senators announced a proposal calling for the U.S. to reduce oil demand by 40% by 2020, which is definitely an ambitious goal. To reach that target, the Democrats said that by 2010, 25% of the cars sold in the U.S. should operate on alternative fuels. Now, there's a lot of proposals in the Senate. One of the more interesting ones is something come up from Barack Obama. He has his own approach. He would require the world's big oil companies to invest 1% of their quarterly profits in renewable fuels. Now, I can only guess what the Republicans would say about this. They'd say it's a tax on the oil companies, and it would be really a tough one to pass. But it's an interesting proposal. Now, I'm mentioning all these bills not because I think they'll pass under the Democrats, but to show you a wide variety of the proposals that are floating around in Washington right now. However, next year, Congress is expected to pass another huge energy bill, and it's called the Farm Bill. U.S. farm programs basically lock farmers into growing corn, soybeans, all the other products that are getting subsidies right now. There's no room for switchgrass or other potential energy crops at this point, but the new Farm Bill could change that. And lobbyists have already begun for new subsidies for all kinds of crops, from willows to fast-growing poplars. As a warm-up act for the next year's big farm package, the House Agriculture Committee recently passed a resolution calling for 25% of the nation's total energy supply to come from renewable sources, such as solar and biofuels. And that deadline for that would be 2025. So 25% of all of the energy from the nation by 2025. It was just a resolution, not a mandate, but it really showed sort of like the sentiment going on in the Energy Committee, or in the Agriculture Committee right now in the House, and I suspect probably in the Senate as well. There is widespread interest in both political parties to including an energy title in the Farm Bill. A sideline to that, when the Agriculture Committee was passing that resolution, there was a representative, Mike Conaway, who's from Texas here, a Republican from Texas. He tried to include language that said the market is best suited to determine which forms of renewable energy are most effective. In other words, he wanted to basically say, no subsidies, let's do it with the market process. But that provision was dropped before the resolution was passed. But in fact, the current House Agriculture Committee chairman, Representative Bob Goodlatte, a Republican from Virginia, also has vigorously advocated a more market-oriented farm policy. He wants to totally overhaul the bill. But if the Democrats take control of the House in November, Goodlatte would be replaced by Democrat Colin Peterson of Minnesota. Now, Peterson was one of the first persons in the House to call for extending the 2002 Farm Bill, basically in the same structure it is now, but updating it. One of the first farm bills to be proposed so far came from Representative Ron Kind of Wisconsin. It was called the Healthy Farms, Food, and Fuels Act. So in other words, the fact that they put fuels up there in front and center was pretty important. Among other things, it would increase the annual loan guarantees for development of renewables on farms from $20 million to $2 billion. Now, the Farm Bill is a complex mix of agriculture policies, much of them made up of wet kisses for various crop programs. But it also includes the Habitat Conservation Program. Somebody made an allusion to that this morning. What that does is it pays farmers not to plant crops on some 39 million acres of land in the nation. Most of those lands are located along waterways, rivers, streams, or are in sensitive environmental areas. Taking them out of production is thought to reduce sedimentation in rivers, it establishes wildlife habitat, and it enhances forests and wetlands. Well, this land is smack dab in the middle of the ethanol debate right now. Some farmers want to begin growing corn on their land, corn or other biofuels, because they see this as an opportunity. Nobody's using it. We need corn. Let's grow it here. And you can imagine the environmentalists don't like that idea. The wildlife groups don't want to lose the habitat. And in fact, the hunters are among the biggest supporters of the Habitat Conservation Program because that's where all the wildlife is. Now, Colin Peterson, who would be the chairman of the Agriculture Committee under the Democrats, has proposed expanding the land and conservation programs and allowing farmers to grow switchgrass or other, biofuels, but not corn particularly, on some of the new lands. Now, this issue is going to be hotly debated in the next Congress in the Farm Bill, and it could impact how much land is available to grow biofuels. So the question remains, will Congress pass any legislation to help the ethanol industry next year? Well, it helps that you have some powerful lobbyists behind the ethanol industry right now, and growing number, I think. The House resolution passed this last week, the one that called for 25% of the nation's energy to come from renewable sources by 2025, was a brainchild of a lobbying group called the Energy Future Coalition. They created a 20 by 25 coalition, which has the potential to be an impressive lobbying force this next year. Right now, they're working on putting together a master plan aimed at the Farm Bill. Their agenda goes beyond biofuels. It's also solar and wind and other things as well. The group has an interesting makeup. It's made up of farm groups and the car industry, several environmental groups, the American Banking Association. On the Republican side, it's got Newt Gingrich. On the Democratic side, it's got John Podesta. And it's got all the Western governors. So it could be powerful. But that's just the tip of the iceberg on lobbying. I think we're going to see a lot of it next year, and you'll be hearing about it. But the new legislation for ethanol is not a slam dunk. Not everyone wants to give more money to promote the biofuels industry. Some conservatives in Washington want to eliminate the entire price support system for agriculture, including anything that would go to ethanol. Legislators from oil states don't look at ethanol as a warm and fuzzy issue. They'd oppose a lot of the legislation that's been proposed by the Democrats and stuff that's been proposed by the Republicans. Bill O'Keefe, who is a former lobbyist for the petroleum industry, recently wrote that federal tax loopholes are creating an artificial market for ethanol. He argued those subsidies are stifling other new technologies for cars. And if the price of oil goes down any more than it has already, Congress will be likely to feel pressure from the people, will not be feeling pressure from the people back home. So they will not be as interested in passing something big for the ethanol industry. And unless they're in the middle of the Iowa cornfield, then they'll continue to care about this issue because ethanol is being looked at as a salvation for the farm states. So in conclusion, ethanol, biofuels, are going to be front and center in the next Congress. No matter who controls the Congress, for the next 2 years, the ethanol industry will have friends in Washington and some enemies. Thank you. Should we just go over it next? Sure.
Thank you. I guess I'm the only person that separates between you and the reception, so I'll bear this in mind. The perspective that I bring here is the recent influx of energy security or national security groups that have joined the debate on biofuels and energy in general. These are folks that are there because they believe that we cannot win the war on terrorism as long as we are paying for the other side. And these are not the kind of people that are interested in a sort of 1% solution or 2% solution that we have today. If you tell me as a national security advocate that we can go up from 2% penetration of biofuels to 5% or 6%, that to me is like somebody who smokes 100 cigarettes a day and he goes to 95. He's still going to get the cancer probably. But so I think that the question that we really need to ask ourselves is Is the whole thing for real? Can we really utilize biofuel as a real alternative to our oil dependence? Can they make a difference? If so, what are we going to do to make that happen? And of course, is our government capable and willing to do it? My simple answer is to question 4, a qualified no. I think that our political discourse around biofuels and alternative fuels in general is marred with fallacies, myths, exaggerations, and sometimes outright lies. And I will try to touch some of those issues here. Let's take, for example, the issue that we discussed about this absurd that we have a system in which we don't tax fuel coming from all those guys that you see here, but we do tax alternative fuel coming from friendly countries. And as Margaret suggested here, the reason is that we have a bunch of people who, with presidential aspirations, who need to march through Iowa and read from the Mao's Red Book. And they know that they don't have a chance of being candidates if they don't pay a tribute to the ethanol lobby. Now, this is a good example of this. This is a picture, 2 pictures from 2 press conference, 2 presentations of new bills from last November. The Vehicle and Fuel Choice for American Security Act. These are, it's a bicameral and bipartisan effort. I agree with Margaret that in order for anything to pass now, it needs to be bipartisan. And I believe this, what you see here, is the only game in town today, because it's the only truly bipartisan effort. The Senate bill has 28 senators on board, ranging from Sam Brownback to Evan Bayh and John Kerry and Hillary Clinton and many others. And in the House, there are almost 90 House members. But the interesting thing is that the House effort is led by Congressman Jack Kingston, who is, according to Nation magazine, the most conservative House member. And these 2 bills are almost similar. They lamp up many provisions that add up to an oil saving of 2.5 million barrels within 10 years. But the difference between the 2 bills is that the Senate bill does not have the provision that removes the tariff, whereas the House bill does. And apart from this, they're almost identical. So it shows you that politics, domestic politics, plays a huge role in the way that we can really get something done here. Now, there are 2 things that are very agreeable, I think, and that is the infrastructure issue. I think both the people on the right and the left accept the notion that, if we do want to have significant market penetration of alternative fuels, we need to provide the infrastructure. I think this is relatively easy to do, both in terms of cost and as well of political feasibility. The other thing is flexible fuel cars. I think this is because the auto industry is pretty much on board. We can discuss the numbers, but the overall concept, the cost, it's about $100, $150 per car. It's not a huge investment, so it's a really low-hanging fruit. But here is a big but. My feeling is that we are making today a huge, huge mistake by encouraging flexible fuel cars that can only run on one type of alcohol. And if we are serious about an alcohol economy, or using alcohol as the new currency that can substitute for oil, it is critical that we begin to think beyond ethanol. Ethanol is not the only alcohol. Methanol was mentioned here a number of times today as a fuel component for biodiesel, but methanol is a fuel in itself. It can run in flexible fuel cars. In fact, if you go today to China, you see that 8 provinces in China just shifted to methanol. They're building today over 80 coal to methanol plants. And there is no reason why, if we talk about fuel flexibility and why shouldn't we have real fuel flexibility so that every alcohol can compete in the market? Now, bear in mind, methanol is not a perfect fuel. It has its own drawbacks. Some people say, it's toxic. It's true. If you drink it, you're in trouble, so don't drink it. But it's not a beverage. And today we know how to fuel cars with fiber optic nozzles that are spill-free. By the way, ethanol is also toxic. It is denatured, and don't drink it. So does gasoline. Methanol has less energy packed in it. It has, but on the other hand, it has other advantages. For example, it has less carbon. But the most important advantage of methanol is that it is far more scalable than ethanol, in the sense that it can be made not only from agricultural material, but also from any other carbon-carrying substance. It can be made from coal, natural gas, of course, all the biomass that you can make ethanol from. If you read George Orwell's latest book, The Methanol Economy, you'll see he has a whole theory about how you can make methanol from CO2, et cetera, et cetera. So I think that we really need to open the door wide to all the alcohol. Interestingly enough, a lot of people are talking about the conversion of biomass into ethanol. Nobody's talking about conversion of biomass into methanol yet. When we do the conversion, you see that 1 ton of biomass will yield you more, almost 50% more ethanol as a fuel than more methanol than ethanol. And the other difference is that if you go methanol from biomass, you're using chemistry, whereas if you go the ethanol route, you use biology, you use all kind of genetically modified biocatalysts, etc. This is not a technology that is ready for the market, whereas with chemistry and gasification, we don't have any technological barriers to the degree that we have with conversion of cellulose to ethanol. So I think that, the important thing is that we need to keep all the options open. And what our government is doing today is exactly the opposite. Our government is telling us that there is only one alcohol that can compete in the market. This is not the role of government. Government should not, and if you see the latest energy bill, you see that how many times ethanol was mentioned and how many times methanol was mentioned. Clearly, there was a whole ethanol title in the energy bill. There is a lot of money, but it's clear to me why it is, because methanol is an orphan fuel, whereas ethanol has so many political advocates. Just like we go to the bar, we don't want the bartender to tell us that we can only have scotch and we cannot have vodka. Let's go back to the issue of ethanol. And I think that one of the things that there is a lot of talk about cellulosic. Cellulosic is not ready, and we don't know when it will be ready. We hear all kinds of stories, but the reality is that there is not one single full-scale demonstration project that can tell us how much it cost, what is the input, what is the output. We don't know. We also know that corn is limited. We've talked about it. We know that there is a scalability problem. And we also know that under these conditions, right now, if we're really serious about deployment of ethanol as a fuel, sugarcane is pretty much the only game in town. And that sort of brings the debate in Washington to a whole new level of those advocates of energy independence versus the advocates of energy security. The two different concepts that we need to differentiate between. Energy independence people want us to produce everything and not import anything. Energy security people like me believe that there's nothing wrong with importing ethanol from Nicaragua or from Belize or from Guyana or India or Africa. We don't have any problem with that. So I think we have two schools of thoughts that advocate different things here. Of course, sugarcane has huge advantages in terms of energy balance, in terms of cost, in terms of scalability. I'm not going to go into the details now, but it's very important to understand that if we are really serious about bringing ethanol to the road, to the gas station, this is the only way to go now. Later on, God knows. But right now, and we don't have time to wait, this is the only thing that we can do. Ramp up production, send our money to, instead of to the Middle East, to the developing world, and do it in a way that will be environmentally friendly and all the things were raised here, but otherwise we're all living in one big illusion. Let us not delude ourselves to believe that we can have significant market penetration under the current circumstances. Furthermore, 70% of Americans have no access whatsoever to ethanol. And unless we begin to bring ethanol to places like California, East-West, the South, it's going to be a boutique fuel in the Midwest, and we're not going to get much more than that. And that's why it's so important to open those import routes and begin to barge in ethanol from other countries. Otherwise, it will go to other countries. It will go to China, it will go to Japan, it will go to... There's enough market for ethanol. If we don't buy it, someone else will. The other thing that and I agree with somebody mentioned before, that we're building a lot of corn ethanol plants. Nobody is really checking how much corn we can produce to feed those plants. I think we're going to go from boom to bust pretty soon. One of the reasons that we're facing this problem is, if you look, we're dealing with a very serious misallocation of resources when it comes to corn. As you can see here, from the Department of Agriculture, most of the corn in this country is used for animal feed. In other words, the cows that make your steak are being fed with corn. That's not what's supposed to happen. Cows are not supposed to eat corn. They're supposed to eat grass. So what we have today is a very, very bizarre situation that we send most of our corn to the cows so they can eat something that they're not supposed to do by nature. And then we want to ramp up production of ethanol. So what do? We grow grass. But the cows should eat the grass. That's exactly what nature tells us to do. The cows need to eat the grass, and then we can allocate more corn for ethanol. That's how nature designed the system. But we sort of have a very, very distorted situation here, that we created an agribusiness that has committed corn to the animal feed. By the way, the rest of it, as you can see, some of it is going to export, but even when it comes to our food industry, we don't use sugar anymore. We use high fructose corn syrup, which is one of the reasons that we have so many obese people in this country. And so many other issues. But if we really need to sort of understand the flaws of our energy situation, we really need to understand the nature of political system. And our political system, and I always am asked the same question: what is the single most important thing we need to do to improve our energy security situation? And my answer is always, take the primaries out of Iowa. Nowhere in the Constitution, nowhere in the writing of our founding fathers, it said that thou shalt go to Iowa and become the next president. We need to understand what we are paying in terms of energy security, public health, and other things, related issues, for the fact that we are every 4 years sending our future president to be elected in Iowa. One more point. One of the things that always amazes me is how dogmatic we are and how simplistic the debate in Washington is. We're talking about E85, and somebody raised the issue E85, said it's not enough, we need to do E95. E85, the reason that they chose the number 85% is because that's what you basically need to get the optimization between having the maximum amount of ethanol and still having the ability to start your car in the winter. But fuel flexibility allows you to use much lower blends. And we have two modes, E10 and E85, and nothing in between. The problem with E85, as you can see from the latest consumer report, is that if you drive your car on E85, you have to refuel more often. People don't like to go to the gas station. And you compromise your range. But the other problem is that and I listened to Andy Karsner saying is that his boss is talking about creating a national market for ethanol. Now, if you really want to create a national market for ethanol, that means that you need to have more people using less ethanol rather than a few people using a lot of ethanol. That's how you create a market, by by progression, just like it happened in Brazil. They did not start with 25%. They started with increments, and over time, people got used to it. They saw that it's for real. You know, things happen. We want to go from 0 to 85% overnight. It doesn't work that way, and in fact, it's only going to create a situation people will. It will backfire on us, I think, because it will. People will not be happy with the fact that they have to refuel their car so often, and I think that we'd be better off if we have the fuel flexibility, if we have the flex fuel car, to start with a blend that is high enough to prevent environmental problems, and yet low enough to have spread the butter thin across the country so that more people get the ethanol experience or the alcohol experience. And I think that we must have other alcohols in the mix. In some parts of the country, it will make sense for people to use methanol. In some parts of the country, it will make more sense to use ethanol, depending on what state you are, depending on what are the energy sources that this state has. This is sort of my last slide. It sort of maps the various interests here. Set America Free, the coalition that I'm one of the founders of, is defined as a coalition of tree huggers, do-gooders, sod busters, and VCs, evangelicals, and cheap hawks. Cheap hawks meaning those who want to win the war on the cheap. As a representative of the cheap hawks, we always look at this and say, are we going to take this $5 billion and use it to create more ethanol? We're going to use the $5 billion to build another aircraft carrier. That's the kind of trade-off that we have, because we are simple-minded people who care more about the melting of the West than the melting of the ice caps. But the issue is that what you see here is that you have a lot of people with favorite approach towards biofuels in general, but they come to this from a very different perspective, and they have very different interests in mind. And those interests don't always play together very nicely. And those interests, if you are a cheap hawk, you want everything and right now, and you don't care if it's made from coal, natural gas. You have a war to win. If you are a do-gooder and you care about the poverty and the developing world, you care about food costs and all kind of other things. If you are the agribusiness, you want to. And by the way, somebody mentioned in the morning about the farmers. The farmers, and particularly the agribusiness, I'm not sure at all that they really want the ethanol market to grow. I think that they want it to be small, protected, for as long as they can have it small and protected. Of course, they make the noises and they talk about 25 by 25 and 35 by 35, all these big numbers. But I judge people what they do, not what they say. Every single senator and congressman has a flary speech about the need to become energy independent and throwing all kind of numbers. And they talk about Manhattan Project and Apollo Project and all these big, big, big words. But it's very important to understand that those politicians, most of what they do is messaging. Most of what they do. A politician likes to go to his voters and say, I introduced a bill. But I look at how many people co-sponsored the bill, and who are those people? If you have 40 co-sponsors and all of them are Democrats, that's not going to get you anywhere. If you say, I did a Manhattan Project bill, but you are the only co-sponsor of the bill, that's not going to go anywhere. So we really need to look at those political proposals that have two things they need to have. Three things. Number one, they need to be bipartisan. Number two, they need to be bicameral. Many, many times it happens that Senate had a very good bill that was killed in the House and vice versa. Number three, they have to be approved by the committee chairs. And what we have today are two very problematic committee chairs in the House, Congressman Barton and Congressman Dingell. One is the dog watch of one works for Big Oil, one works for Big Auto. And they feel that they passed an energy bill last year, and there's no big rush. There's no they can sit on the laurels, and they don't need to pass anything anytime soon. They're getting a lot of pressure from beneath, from people who are facing a lot of tough questions in the district. And I think that as we're moving towards the next session, we will see more and more people coming and knocking on their doors and say, we need to do something. Now that will happen when we have a combination of unfortunate events, when we have a combination of a terror attack in Saudi Arabia or a war or a hurricane or God knows what. But we're living in a very, very tight energy market in which any day something bad can happen that can send oil prices through the ceiling. At that point, there'll be political momentum to do something. And those proposals that are out there will galvanize into a piece of legislation that will be accepted by the majority of those people. And I think that it will have a very, very important component of biofuels along the lines of what I say, along the lines of what this vehicle and fuel choices bill, for a very important reason. It sits very well with Republican mentality of free market and open market and choice. Because what this bill does basically tells you that you have an inherent right to choose what kind of energy you want to use for your transportation. Whereas today, 97% of our transportation energy is petroleum-based, so you don't have the choice. You have gasoline, 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 and that's all. This bill is changing this, and it basically tells the government to open the door and allow free competition so that every new car sold in the United States can run on gasoline and something else, but we don't say what it will be. And by stimulating the market to work, by creating this kind of competition, by introducing new players into the transportation fuel market, we can create a situation that we may not be energy independent, we may not have energy security anytime soon, but at least we have an insulation that we need for if and when something bad happens. Thank you.
Okay, well, thank you very much. You guys want to come up to the chairs for a second and see if we have any questions from the audience?
Quick question on the thing of the tariffs. I've been following I happen to have satellite, we have RFD TVs on there, and they've been following the trade thing for farming. As I understand it, because of the international negotiations that's going on, most of the subsidies are gone anyway. So, you know, is that going to have the same impact? You got up there, don't touch our farm subsidies. From what I understand, that's not going to be an option. The subsidies are going away. The question is how or what they're going to be converted to. And that's going to have an impact on how they do corn and all the other products.
I know there's a lot of debate on the WTO, the World Trade Organization, over farm subsidies. The notion is that all of the countries should eliminate their farm subsidies.
By 2012.
Pardon me?
By 2012, I think.
By 2012? Well, I'm not sure. You know, the people on the agriculture committees are still looking at those subsidies. I mean, they'd like to continue them, so I'm not sure how that's going to play out in Congress.
Melvin, do you have a comment on that? Comment from
The European position is very clear. We have no subsidies for anything other than perhaps olive, where we might get depopulation if we stop putting direct aid. Everything is decoupled. Farmers only get aid if they do what we call Pillar 2, which is environmental improvement. So in theory, they could farm only the environment and produce nothing and get their aid. What they can't do is produce crops and not do anything environmental if they want any aid. So the aid is gone as far as we're concerned. You and one or two others are the few people that still have it. The Australians don't have it, the New Zealanders don't, and so forth, and that's certainly the way it's going.
I anticipate a huge battle.
I thought the term you used, Ms. Kritz, was the jurisdictional disputes that were coming, and I think that's a very interesting one, because with this 25 by 25 vision where agriculture is no longer just food, but it's becoming energy, and there's all these environmental implications, it just seems like it's a real food fight between EPA, USDA, DOE, we could probably name some more, as to who's on first or who controls, and I'm just wondering if there's anybody looking out. I mean, this is a train wreck, it's happening. You know, we're caught in this, you know, this labyrinth, if you will, and it just seems like, you know, we need a different model. The system we have now will not deal with these complex solutions very well.
I think you're right, but you have a jurisdictional dispute because there are jurisdictions, there's committees in the Congress, and the people who have been there have seniority, and they've been there a long time, and they know how to protect their people from back home. The Farm Bill is interesting because you can do a lot of things on the Senate floor, let's say. You can just have a plain Farm Bill that will go through the Ag Committee, and it gets on the Senate floor, and man, they want to put an environmental this, and they want to put an energy that, and so it could become kind of a Christmas tree for all kinds of different pieces. But I know that there are people who want to eliminate all the subsidies, but at this point, the people I was talking to on the Hill, they're going.
Don't forget that
95 miles an hour forward.
The chairman of the Finance Committee is Charles Grassley, better known as Chuck Cornley, the senator from Iowa. And he is the guy who's responsible for all the tax provisions, which brings me to the second recommendation after moving the primaries from Iowa, to introduce term limit on committee chairmanship. I think one of the problems we have today is that committee chairs sit on their chair forever.
No, they have term limits.
They have,
both sides of the
they have, but they never apply it.
Yes, they do.
Well, only
Every 6 years.
Yes, but if they are removed from power, if they become a ranking member, it resets the clock.
Oh yeah, that's true.
See, so what you have today basically is two people playing musical chairs, and you end up with the same people all the time. And they normally work very close, so because they have aligned interest
It
here.
depends on the party, who the two individuals are. I mean, you're right about John Dingell, who's the Democrat, who would be the chairman on the House Energy and Commerce Committee, and Joe Barton, who is a Republican from Texas, who is now the chairman of the Energy and Commerce Committee. They do not see eye to eye on everything.
Not
They
everything.
see eye to eye on the energy bill. But one of them is blue-checking big oil, and the other one is very supportive of the car industry that just happens to be in his home district.
Right, but ask yourself, why is it that the chair and the ranking member of the Senate Energy Committee comes from the same state?
Yeah, that was just a matter of both of them being on the committee and having the seniority as they went up.
So these are the kind of things that what I'm saying is there are structural issues, political issues, structural issues that need to be addressed because they are creating all kind of deformities and problems, structural problems that cannot be solved under the current system.
This is a question for Gal. You said that all cars sold from now on should be flex fuel. Do you also advocate that we keep the flex fuel credit because the cafe standards really have become a joke, number one. And the second question is, I don't see us, having the sources for all this alcohol. We're going to have choice, but we're going to have no availability.
Okay, so the first question is, and I'm sorry that the woman from Ford is not here, because when you look at the production of flex fuel cars in the United States, you see that only the big gas guzzlers are FFVs. We don't see small cars can run on ethanol, right? Now why is it? Because the auto manufacturers, they get CAFE credit.
3.5 liter engines and above.
Right. That's not because small cars cannot be flex fuel cars. It's because the autos, they get CAFE credits for putting FFVs on the road. And the bigger the car, the more credit you get. Now, what it does is, this is a loophole that causes more people to use FFVs, but they don't have the fuel, so they use gasoline, so you end up using more gasoline than saving gasoline, which is a very bad loophole. And that's why I think that fuel flexibility should be applied across all car models. And by the way, fuel flexibility is not only alcohol. A plug-in hybrid car is a flex fuel car because it can run on gasoline and electricity. So I'm not.
But I can't buy it, basically.
Not now, but it's in the making. As for alcohol, look, if we stay with agriculture, with plant material, I don't think that we can really reach significant market penetration. At least not that market penetration will make a difference to the things that we care about. Big difference. Okay, in the margins, but it's not going to stop global warming. It's not going to stop the geopolitical problem. It's a feel-good type of thing. If you really want to do alcohol, I don't see any way other than beginning to make alcohol from coal. Coal has to be part of the equation, and it should be part of the feedstocks. And by the way, the environmentalists are freaking out now because all of a sudden they realize you can also make ethanol from coal, which was something that was so beyond their comprehension. But all of a sudden, coal companies say, we can also make ethanol as well, and just no. We love ethanol, but not from coal.
Well, another problem is that it means if you're worried about greenhouse gas emissions, it's double the greenhouse gases. First when you make them, second when you use them.
I'm just going to comment. I think there's danger in pitting ethanol against methanol or any of these alternatives against one another. I think all that does is fuel the other side. And I think you really have to look at all options and take them strictly on what they can contribute, what the merits are. But I think, for example, you pointed out that you can make more methanol and ethanol, but if you take the energy content, it's about the same.
All I'm saying is, I'm not saying which one is better. Each one has, and I'm not playing the one against the other. All I'm saying is, today we have a system in which there's only one alcohol in play. That's it.
No, but your comments do come off one against the other.
Well, I'm trying to balance a system that is heavily rigged in favor of one alcohol. And I'm saying we need to have a much more balanced approach and allow everybody to compete on an equal footing. And then whoever is better, I don't want to tell you what to use. You want to use ethanol, methanol, I don't care. But don't limit, don't tell me what, it's like they're doing the same thing that they've been doing with hydrogen. The two energy carriers, one is called hydrogen, one is called electricity. Our government has dictated to us that hydrogen is a better energy carrier than electricity. If you see with the allocation of funding, if you see the government R&D, everything, the president speeches, the Secretary of Energy, they have dictated to us that there is one solution that they like, and all the rest are not in the same in competition. This is not the role of government. Government needs to open the door wide so everybody can compete and let the free market decide which is better. And I'm not saying which is better. I'm saying I think that true fuel flexibility and true fuel choice requires equal treatment for all the liquid fuels, and let the market decide which will be the more popular one.
Okay, we get two last comments and then it's time to go relax. Go ahead. Yep.
Thank you very much, both of you, for the presentations. I see a very sort of a dogmatic and sectarian approach here. I agree with Chuck Wyman on that one. But the question I have is, why is it in both presentations, which is in a way a report from Washington, why is it that I haven't heard any reference to doing something about the demand side? Everybody talks about the supply side of things, but nobody ever thinks that, do we really need an additional supply of fuels, or can we do a better job of using the fuels that are available to us? Isn't the demand side perhaps sort of an inconvenient tool, but an effective tool against threats from abroad in terms of availability of this country to function?
Well, I think that CAFE standards were supposed to be the answer, but they haven't been raised significantly or even notably for a very long time. If you were to see a bill that would mandate higher CAFE standards, it would be vetoed. And everybody on the Hill knows that. Right now, the Republicans hold the House and the Senate, so nothing has gone anywhere.
Could it be
even if the Democrats win the House, then you have John Dingell from the Energy, would be in charge of the Energy Committee, and he has people back home that work for the car industry, so he's not interested in CAFE standards.
But they may not survive beyond the next 5 years. I mean,
Who's that? John Dingell?
No, well, John Dingell will survive, but Ford and General Motors.
They're making a call in effect, I'm not gonna say it.
You're right, but there is another dimension here, and I think that sort of, we need to put a mirror in our face, and I think that the real story with the kind of things that demand management is that we don't want to make sacrifices here. We like to talk about our energy security problem, but we don't want gas taxes. We don't want to be told in what speed, in the state of Texas, just raise the speed limit.
To what?
It's 80.
120.
100?
No. Let's just say we're going above 55 here.
I don't know, but the point is, you know, we all like to talk about the problem, but nobody wants to make any sacrifice on the country. So, an election year, going to people and asking them to make sacrifice is not exactly the safest way to be elected. So I really think we all need to sort of look in the mirror and understand that this problem cannot be solved without some sacrifice. Some, not necessarily a lot, but some. And unless we're willing to make that sacrifice, we're going to be here every year talking about the same problem, and the price will go up, and we're just going to be worse and worse.
All right, you're wrong, you have the last word, go ahead.
Okay, I'll ask you a question that is a number question, okay? Quiz. I don't live inside the belt, so I'm from out of town, which qualifies me as an expert, right? So, I'll quote the late Rick Smalley, that in many conversations I had with him, we kind of coined the phrase that to really make a change in the energy equation of this country, you need sources that are in the range of tens or maybe 100 terawatts. 100 terawatts, a terawatt is 1,000 gigawatts, which is more than the size of an average large power plant. So we are talking about, to make a change, about 100,000 new large power plants. The number that I'm missing here, and I wonder if it's floating around in Washington, is what is the ultimate potential of biomass? Because I can tell you that
For electricity or biomass?
any form of energy. I can tell you that photovoltaics has 100 terawatts because the sun is bombarding the earth every day between 150 to 200 terawatts. Mining the heat of the earth has got terawatts. What is the ultimate potential of biomass? And I wanted to float this question, not necessarily to your panel, but
Why don't we leave it as the thought for tomorrow?
yeah, I would like to hear people.
Okay.
Right, because
Yeah.
nobody knows.
Yeah.
All I know is that a few weeks ago I went to a convention of the paper industry, and everybody was complaining that they don't have enough cellulose. So I'm asking myself, if those guys don't have enough cellulose, so what's wrong here? On the one hand, we hear how we're going to soon convert all our cars to run. But the short answer is nobody knows, because it all depends on how you factor it in, which qualifies, which kind of cellulosic material complies, and how much of it is economic. You need to plow some of this back into the soil. Some of it is, just to get it from the field to wherever it's needed, takes more energy, and it's completely not economic. That's the kind of thing that you get thousands of different answers, and you won't come out of it more educated than you were. So nobody knows.
But you can estimate an upper bound. What's the land productivity?
That's what I'm asking.
And I'll do it tomorrow.
Okay.
Okay, very good.